The concepts of fluxes, hydrological and heat flux exchanges, obviously lead to density changes both in the atmosphere and the ocean. And considering both media are stratified, so density layers are stacked up in the atmosphere with decreasing density, in the ocean with increasing density from the surface, you can create buoyancy changes, and because you are in a stratified media, those buoyancies will be relative to the environment above and below. So the concept of reduced gravity arises. Looking at the vertical motion, it can be a balance of gravity and pressure change. So in the atmosphere, pressure is decreasing with height. In the ocean, pressure is increasing with depth. So here you can perturb the density and create a buoyancy change and a vertical motion, right? So here a small perturbation where the perturbation is much smaller than the mean density. So if we are looking at sigma of 27.9, the perturbation will be about 0.1 or so, let's say. So W is the vertical velocity, is the vertical acceleration, dW dz. It's the vertical motion with height, not the time. And force, the buoyancy force B per unit mass. So the perturbation pressure of the parcel P prime adjusts instantaneously to the ambient pressure P of the fluid surrounding the parcel, so that dP prime dz is dP dz equal minus rho g. Where does this arise? Basically, if you assume for all practical purposes that the ocean and the atmosphere are in hydrostatic balance, then whatever perturbation you do, there has to be an instantaneous adjustment of the movement of the parcels to come back to hydrostatic balance. That's where this equation, this restriction, constraint, whatever you want to call, comes from. So noting again that rho prime is less than the background environmental density, this can be written as buoyancy G equals rho 0, the reference density or the background density, minus rho, the parcel density, divided by rho 0. So this is a relative buoyancy with respect to the density above and below, essentially, because if you think about a vacuum where you are dropping something, then the gravitational acceleration is derived, as you know, in that sense where there is no relative density, whereas here the sinking and rising is with respect to the background density. So that's what gives us a reduced dense gravity as opposed to gravity. So let's transition that into zonal variability of buoyancy induced by radiative forcing. So heating and cooling are the main forms of generating density perturbations. So the radiative forcing here is in equilibrium as a function of latitude, so zonally averaged meridional section, time averaged as well, is a function of the solar radiation coming in and the infrared or long wave being lost. So going to our hydrostatic equation, which in this course we are writing for the first time other than the module that I added from another course, dP dz is minus P over RTG, where what we did was take dP dz equal minus rho g and replace rho by P over RT, because air is considered an ideal gas even with water vapor. Okay, so you can integrate this and get Pz, pressure as a function of height. Okay, this is where the ideal gas comes in handy. Instead of looking at temperature stratification as we mostly do in the ocean, in the atmosphere it's more convenient to look at the pressure which drops off with height, with the reference pressure times exponential of minus g over RTz. For those who have seen this, you already know that this leads to a scale height and so on. But coming back to the mean zonal distributions for seasons and for the annual mean, we are looking at top of the atmosphere net solar radiation here for December, January, February. Obviously sun is to the south, and you are going to get a peak in the southern hemisphere, whereas for June, July, August sun is in the north, so you're going to get a peak in the northern hemisphere. And you can again see the hemispheric asymmetries in terms of the radiation reaching the this is top of the atmosphere. There shouldn't be any asymmetry there. So look at the annual mean. Okay, so you can see again the radiation distribution is now what we expect when we average the equinoctial and solstitial season. Okay, this is emitted terrestrial radiation, annual mean, and December, January, February, and June, July, August. Again, what do you remember? You remember that the ITCZ tends to be cold, so you get minimum in outgoing long wave radiation because of the deep convection creating cold cloud top temperatures, which reduce the outgoing long wave, obviously. And if you look at the net radiation, then the difference of these two, you're going to end up with this, which looks much more like this, with little changes here. Okay, so this is going to create buoyancy distributions, and you can look at the value of pressure as a function of height for two isothermal columns with temperatures of 300 and 275 Kelvin. So what are we doing? We are using now pressure as a coordinate in the vertical, and we are looking for isotherms on pressure surfaces. Okay, it's better seen with the figure, which we will come back to later on, but you can imagine that height is decreasing with pressure is decreasing with height, and the temperature isotherms are dropping off towards higher latitudes because you have warmer low latitudes and colder compressed atmosphere as you go to high latitudes, and the pressure surfaces are doing the same as well. So this is assuming that the atmosphere has a constant lapse rate of minus 6.5 Kelvin per Kelvin. Looking at height of 0, 5, and 10 kilometers, temperature of 300 and 275, 300 Kelvin at the surface, at 5 kilometers, and at 10 kilometers. This is the delta P in the meridional direction associated with these isotherms. And if you look at 275 Kelvin happening at the surface, and then it's happening at a lower pressure hectopascal at 5 kilometers and also at 10 kilometers. This is too confusing maybe, so we'll just come to the figures later on. So you have to imagine these pressure surfaces in the atmosphere. It turns out to be a very convenient vertical coordinate to use. That's why this is done, but I can see that without figures this is not so helpful. Going back to our hydrostatic equation in terms of temperature, we can write pressure difference at same height. Okay, so you are thinking about pressure surface, which is higher in the low latitudes and lower in the high latitudes. So pressure is the same, but the height of it varies with latitude. Also can vary with longitude, as we will see. And we are talking here of meridional direction. So P2 at the same height minus P1 at the same height over a latitude, delta y, which can be written as P0 or delta y exponential minus g over r T2 minus T1z using our hydrostatic relation that we saw before. I'm not going to go back, but basically we converted this one into temperature and r using the ideal gas law. So why are we doing this? Essentially, this is saying when you have small perturbations, delta Z is going to be approximately equal to delta P divided by rho G. another way of saying the hydrostatic relation, but we are going to relate now the meridional gradient of temperature to changes in pressure with height. Okay, so we looked at this before, where we said there is meridional temperature gradients that we have looked at, and this is showing us meridional and vertical gradients of zonal and meridional temperatures. Let's just focus on the zonal winds, zonal temperatures, winds, sorry. So zonal winds in the deep tropics are mostly easterlies, so they are negative from the surface to the upper atmosphere. But when we go off, especially beyond the Hadley cell, we had talked about how there is a strong vertical shear with these jet streams, which are stronger in the winter hemisphere, so winter hemisphere and winter hemisphere. And you can see again here DJF, sorry, this is SON, so winter hemisphere, winter hemisphere. But there is a seasonality as well. The entire system moves back and forth as we saw before. And that's associated with this temperature distribution that we saw. But the maximum vertical shear is also associated with the maximum horizontal temperature gradient. Where are we headed with that? We already mentioned that we have what are called thermal winds. In a situation where geostrophic balance happens, in other words, Coriolis effect, rotational effect, is able to balance the pressure gradient effect, you get a flow along constant pressure lines, but this is for constant density. If the fluid is homogeneous, that's what happens. But if you have horizontal gradients and the fluid is not homogeneous, then those horizontal gradients are going to manifest themselves in geostrophic balance as thermal winds or vertical shear. Horizontal density or temperature gradients creating vertical shear because of geostrophic balance still working. What do we mean when we say Coriolis balancing pressure gradient? Basically, we are saying friction is very small. Obviously, Coriolis gets very small near the equator, so it cannot work. And friction near the surface or the mountains is not going to allow a strong balance between Coriolis and pressure gradient. Momentum balance is going to have pressure frictional effects as well. So when you have no friction, steady flow, no time derivatives, and you have these geostrophic balances, horizontal temperature and pressure gradients are going to give us thermal winds. So we'll do the derivation of thermal winds keeping these relations in mind. We have hydrostatic balance, geostrophic balance, and no friction, no steady flow, and horizontal density gradients. Few conditions which are actually met in the world quite a bit in the planet. That's why we have these vertical shears and jet streams.